Okay, so we are going to discuss some more properties of set of reals. One thing you can notice that if we have got two real numbers x and y and they are at a distance, I mean they are far apart such that y minus of x is strictly bigger than 1, then we can see that there exists an integer which is going to lie between x and y, x is less than k less than y. So, we can say that now that between any two distinct real numbers there is a rational number. Let us see how it this. So, suppose I have two real number x and y and x is less than y, however close they are. Now, if they are at a large distance, suppose if x is here and y is here, then as if y minus of x is bigger than 1, then there definitely there is going to be an integer m which is in z, there will exist, that is what we have seen it here. Now, they are very close by, whatever closeness we do not care. Now, what we can do is that this close we just expand them. I mean, if I hit some large number, for example, in this picture, suppose if I hit with 10, then 10x will be somewhere here and 10y will be here. Now, this between 10x into 10y, this is going to be, the distance is going to be bigger than 1, because I can get one integer there. Now, again what I did is that think of it as an elastic one. So, your x and y, you stretch it, you stretch that, then what you are going to get is that you are going to get an integer over there. Now, again you shrink it, that means, so you are going to catch hold of this. Now, if you shrink it, divide it by 10, then obviously 10x will come to x, 10y will come to y, and this m is going to be here, that is m by 10, m by 10 is, so this is what, and m by 10 is a rational number. This is precisely the proof of this theorem, between any two distinct real numbers there is a rational number. So, you take x and y is a real number, and without loss of generality you can take that x is strictly less than y, then y minus of x is greater than 0. Now, by the Archimedean property, there will always exist an integer such that k into y minus of x is strictly bigger than 1. Therefore, kx and ky, they are one distance apart, more than one distance apart. So, there is going to be one integer between them, right. Now, this implies that x is less than m by k is less than y. So, this m by k is a rational number. So, between any two real number there is a rational number. Similarly, what we can do is that between any two distinct real number there is an irrational number. Now, you take x is strictly less than y. By the previous proposition, there exists a rational number r such that if x is a real number, y is a real number, then root 2 x is also a real number, because real number is a field, set of reals are field. Root 2 x and root 2 y are two real numbers. Now, there will be a rational between root 2 x and root 2 y by the previous theorem. Now, therefore, x is less than r by root 2 is less than y, and this r by root 2 is an irrational number. So, between any two real number there is a rational number. So, now we will see the further one. Okay, so, we will now define what is called a supremum. You see, this is something which we will define for a set A to be bounded above, we have a least upper bound property. So, now supremum we will define to be least upper bound of A if A is bounded above, or we will assign the value infinity if A is unbound, it is not bounded above. Similarly, we will define the infimum to be the set of it is the greatest lower bounded below. If not, then we will define it to be minus infinity. So, for example, the supremum of R is infinity and infimum of R is minus infinity. Now, if you look at set of A equal to m by m plus n, where both m and n they are in their natural number, then you can see that of course, this is bounded above. Therefore, this is less or equal to 1. Now, therefore, the supremum is going to be the least upper bound. So, supremum of A is equal to 1 and then the infimum of A, this is going to be 0. So, I urge you to try this problem, I mean try to see that both the supremum of A is 1 and the infimum of A is 0. And so, there is some more property of the supremum, infimum or least upper bound. Suppose I have a set A where the supremum is here, this is what the supremum is. Now, I take a number beta to be less than the supremum, then definitely there will exist some element of this set capital A between this beta and the supremum, because supremum is going to be the least upper bound. Therefore, anything which is less than that number cannot be an upper bound. Cannot be an upper bound means what? There will definitely be an element in the set A which is bigger than the number what we have got, which is less than this. So, this is what. Similarly, for the infimum, suppose I take the infimum here and a beta is greater than this infimum. Infimum of A is the greatest lower bound. If I am taking something more, then that is not going to be a lower bound. That means, there will be an element of the set which is going to be less than that element. So, that is what is the supremum and infimum. In this is what we can write, that you take alpha to be the supremum of A. Now, you take any positive number, then alpha minus that positive number, let us call it epsilon. Alpha minus epsilon is definitely less than, if alpha is here alpha, then alpha minus epsilon is here, or you can take wherever, however close to alpha you can take whatever, but it is going to be a lesser number than that. And so, there will definitely be an element of this which this is great A naught is bigger than this. Similarly, if alpha is the infimum, if this is alpha, then you take any epsilon positive. If you take this as your alpha plus epsilon, then there will be definitely A naught which is alpha plus epsilon is going to be bigger than this A naught. Now, it is easy to see, which you can show it by yourself. If I have two set A and B and A is contained in B, that means B is the larger set than A, then the supremum of B will be bigger than the supremum of A. Supremum of the larger set is definitely will be greater or equal to the supremum of the smaller set. However, if the supremum of if A is contained in B, then the infimum of the larger set will be less or equal to the infimum of A. For example, you take 0, 1, 2, 3 and then you add minus 1, then minus 1, 0, 1, 2, 3, this is going to be a larger set than 0, 1, 2, 3, and because you have more option of going below, therefore, the infimum would be less or equal to the infimum of A. Okay, now, what we have know is that, you see, if we have got x and y, they are in R, then by our prescription we know that x y belongs to R. You see, we may not be able to write down concretely, let us say what is root 2 into pi, we may not be able to write, but what we know is that root 2 into pi is a real number, because R is a field. we can multiply, we have the freedom to multiply. Now, also therefore, if I take a real number, then x into x into x into x into x. So, this is going to be n times I can get a real number, let us call that to be x to the power n. Now, is it true that if I have a real number, then I can take the nth root? That is a natural question. So, what one can show is that if we have a positive real number, then there exists a n, and for every n there exists a unique y such that y to the power n equal to x. In other words, which one can write that y equal to x to the power 1 by n. So, if I take any positive real number, then I can define the square root, cube root, fourth root, fifth root, everything, every 1 by n for any n. So, for a positive real number, I am not going to prove this theorem, but this is this can be proved by using the definition of the real number by taking the supremum of the set. You take the rational to the power this, then that I can define. Now, what we need to define is that supremum of that is going to exist. So, I skip the proof, but this is a fact that for any positive real number we can define the nth root. Okay. So, now let us with all this whatever we have told. So, like what is what you know is that what is a real number. So, every real number is going to have a decimal representation. So, this we are going to prove it by using the axiom what we had defined the real number with the least upper bound property. So, now I take a real number x. So, I take the greatest integer of x, that is less or equal to x. Then this our x is going to be a naught plus y 1, where this y 1 is a positive number which is strictly less than, suppose my x is here, then this is bracket x, then this is something and this is bracket x plus 1. So, this y 1 is going to be strictly less than 1. Now, if I multiply 10, then 10 y 1 is less than 10 and 0 is greater than 10 y 1 is less than 10. Now, denote take the greatest integer of 10 y 1, call it, denote it by a 1. Then 10 y 1, this is equal to a 1 plus y 2, where y 2 is a positive non-negative number which is strictly less than 1. Now, this a 1, because you see 10 y 1 is less than 10 and a 1 is the bracket of 10 y 1. So, what are the possible choice? 0, 1, 2, 3, 4 up to 9. So, a 1 is between 9. So, therefore, what you can write is x is equal to a 0 plus y 1. Now, this is a 0 plus 10 y 1 by 10. Now, 10 y 1 equal to a 1. So, a 0 plus a 1 by 10 plus y 2 by 10. Now, this I can write is a 0 plus a 1 by 10 plus 10 y 2 by 10 square. Now, look at 10 y 2. Now, this 10 y 2, you take this is call it as a 3, then 10 y 2 is going to be a 3 plus y 3. Now, this y 3 is going to be 0 strictly less than 1. So, now what you are going to get x, this is also equal to a 0 plus a 1 by 10 plus this is a 2, because this is a 2 by 10, I am sorry, I have to make it A not A 3, this is call it as A 2. So, this is A 2 plus y 3, then A 2 10 square plus 10 y 3 by 10 cube. You continue like this inductively. So, what you are going to get is every step. Now, obviously, if you look at x minus of a 0 plus a 1 by 10, this is equal to y 2 by 10, which is a positive number. Now, in this case x minus a 0 plus a 1 by 10 plus a 2 by 10 square is going to be 10 y 3 by 10 cube, which is a non negative number. So, if you go up to the stage like n, what you are going to get x is equal to a 0 plus a 1 by 10 plus a 2 by 10 square plus a 3 by 10 cube, a 2 by 10 square plus a 3 by 10 cube, like this a n by 10 to the power n plus 10 y n divided by 10 to the power n plus 1. So, now, so 0 x minus of this is greater or equal to 0, because that is going to be the 10 to the power y n by 10 to the power n. So, this is equal to 10 y n by 10 to the power n plus 1, which is because y n is strictly less than 1, and so this is less than 1 by 10 to the power n. Now, denote a 0 plus a 1 plus a 2 by a 1 by 10 plus a 2 by 10 square up to a n by 10 to the power n is a 0 point a 1 a 2 up to a n. This is the decimal representation of this. Okay. Now, this is the technical part. Now, we consider the set first a 0, next element is a 0 point a 1, next element is a 0 point a 1 a 2, then a 0 point a 1 a 2 a 3, like this you go on. Now, what we claim is that the x what we have started with, this is nothing but going to be the supremum of this set S. Now, as you can see, every step we are going, we are getting a bigger number. This is bigger than this, like. So, now clearly x, whatever n we take, any element of S, then the x minus of this is greater or equal to 0. Therefore, this is lesser equal to x, therefore, x is an upper bound. Now, this set S is bounded above and x is an upper bound. Now, if I want to prove that x is the least upper bound, that means what I need to show? I need to show that I take any number which is less than x. If we can show that lesser number is not an upper bound, then x is going to be the least upper bound, because anything less than x is not an upper bound. So, x has to be the least upper bound. So, that we can show it. If you take alpha less than x, then there exists a n such that 1 by 10 to the power n is less than x minus alpha, because x minus alpha is a positive number by Archimedean property. So, this is what you are going to get, 1 by 10 to the power n is less than. So, we have what we know is that if I go up to, for this given n, if I go up to this addition, then x minus this is less than 1 by 10 to the power n, which is again less than x minus alpha by the choice of R n. This will imply that alpha x x gets cancelled is less than this. So, therefore, alpha cannot be an upper bound for S, therefore, x is the least upper bound. So, this at least you are convinced now, if you start with the definition of the real number with the least upper bound property axiom, then what we know is that every real number has a decimal representation. So, this we can actually derive from that definition of the real number. So, now one can in fact show little more than that. One can show that the rational numbers have not necessarily the every real number will have a terminating finite number of a n, it can go up anything. So, for example, you take 0.33333333. So, this is going to be a real number, and but the rationals will have a terminating decimal thing or a non-terminating recurring. That means, I have some a naught plus a 1, a 2, a 3, a 1, a 2, a 3, a 1, a 2, a 3. So, this is going to be a rational number, and one can also show that the irrational have always will have non-terminating and non-recurring decimal representation. That means, if some decimal representation is given to us, then we see that if it is terminating, then it has to be rationals, because in our class 6 we do this divided by 10 to the power whatever times we go. And if it has a block of recurring, then we also, although it does not terminate, but block of recurring, then we know that this is going to, we can write it in the form of p by q. Now, when there is no pattern, no recurring happens and it just goes on, then that is what the irrational. In fact, some of you must have played the game of how many place value of pi one knows. Okay. So, now so in the real number we have an order. So, what we are going to define is the interval. So, this A, we will call this is A open, B open. That means, the set of all x in R such that A is strictly less than x less than B. Suppose, for example, 0 and 1, if this, then you see 0 does not belong to 0 and 1. Similarly, 1 does not belong to 0 1. So, the endpoints A and B, they are not included in the set, as you can see. Now, we define closed A, closed B. We say that A closed B, if both all these number lying between A and B are there, as well as A and B. Then we call it as open A, closed B. That means, all number between A and B, A is not included, but B is included. So, this we call A open, B closed. Similarly, we can define A closed, B open, where A is included, but B is not included, and all other numbers between A and B are included. A closed, infinity open. So, suppose we say that that is all number which is greater or equal to A. That means, so set of suppose 0 and infinity means what? All this is set of all x such that x is greater or equal to 0. And A open, infinity open, all the numbers between A and infinity, and A is not included in the set. Similarly, we can define minus infinity open, A open. From minus infinity you come up to A, but this is A is not included. So, A here in this case, as you can say, A does not belongs to. And minus infinity A closed, A is a real number. So, minus infinity A closed, which is set of all x which is greater than minus infinity and lesser equal to A. A is included this, for example, minus infinity and minus of 1. If I am taking this, this is open, this side has to be open because minus infinity is not a real number. So, this is minus, so you can say that see that minus 2, this belongs to this set. But what can you say about, so this is my minus 1, then my minus half is here. Minus half does not belongs to this set, 0 does not belongs to this set. Like this, anything which is lying on the right hand side of A, they are not the part of this interval. And the interval with minus infinity to infinity, this is the all the real numbers, that what we are going to call it as the interval. So, these are all the interval can happen only in this type. So, either they can be, first of all they can be finite interval or infinite interval. In the finite interval there will be endpoints, and these endpoints are basically either it is open or closed, depending on that whether you are including those endpoints in your interval or not. In the first A B, no endpoint is included, here only one endpoint, left endpoint is included, not included, right endpoint is included, here the left endpoint is included. And infinite interval, if one of the endpoint is infinity, that is what the infinite. It can be both the endpoint can be minus infinity infinity, or one of them either infinity or minus infinity, then we say that that is an infinite interval. Okay, thank you, and in the next lecture we are going to discuss about the functions which we are going to deal with in this course of calculus. That is one of the most important object what we are going to deal with. So, today let us finish it with this concept of this real number, and thanks.